All right, so we're starting chapter 17. So this is going to be 17.1 vector fields. And we'll be working with these guys for the rest of the class. Okay, so what is a vector field? So we can have vector fields in space. We can have vector fields in a plane. We can have vector fields in any dimension. So as usual, we'll be focusing on the plane just because it's easier to draw pictures. X, Y. So a vector field is, in a way, a function where every point in your domain, so here we're looking at the plane, so the domain is the plane. At every point, you have a vector, all right? So there we go. Something like this. So this would be a picture of a vector field. Every point, there's a vector. So I'll write down some analytical kind of formula examples in just a second, but this is the general idea. All right, we've said way back that vectors, when you think of a vector, it doesn't matter where you place them. A vector is just a length and a direction. For vector fields, usually the vector associated with a particular location, we draw at that location, just as a visual aid in kind of for working with vector fields. All right, let's see. In terms of name, we like to use capitals, and then we like to put an arrow on top. All right, what do these things represent? Well, you can see in this picture that you can represent things like perhaps velocity, right? Velocity fields. So maybe this is we have a river, and at every point you have kind of, the vector would be the direction the water is flowing at that point, and then maybe the length of the vector would represent how fast the water is flowing at that point. All right. So it looks like in this picture, the water is flowing from left to right or east, or west to east. Maybe if I extend this a little bit, maybe for whatever reason, it's flowing faster as we go farther out to the right. All right. Okay. Another application is force. So here's another very common picture that we'll be seeing. So maybe something like this. At every point, again, we have a vector associated with that point, and we usually draw that vector at that point. So this picture here, perhaps it represents again force. So maybe let me call that one capital V, just because maybe we're thinking of it as fluid flow, right? Let me call this, so that would be, this V maybe represents velocity. And this one down here maybe represents force. And this is perhaps represents gravity, right? So you have perhaps a big massive object here, and these vectors represent how much gravity is being, how much the force of gravity from this mass over here in the center is acting on the point at that location. All right. Okay, so in reality, perhaps very far away, the arrows would be very small because gravity decreases in magnitude as you go further and further out. And very close by, it would be very long. Okay. All right, you've probably seen examples, or maybe you've seen examples in physics. You have electric fields, or let's say magnetic fields, right? Perhaps you have a magnetic pole, north and south poles here, and we've got a field like this, perhaps something like that. All right, so these guys are super, super useful, especially since a lot of things in physics are described by derivatives, and vector fields are essentially derivatives, right? Especially right in this, I mean, particularly in this example up here with the V, right? It literally represents velocity, okay? All right, so a lot of things in physics are kind of, a lot of physical properties are given to you in terms of not the object itself that you want to study, for example, your position, but is given to you in terms of derivatives of that. So your position on Earth, right? Where are you going to be if I pick up a rock and I drop it? Where is that rock going to be? The way we figure it out is we have our laws of physics, which tells us acceleration, the acceleration of that rock caused by the gravity of the Earth. And that's a derivative, right? So these guys, vector fields are super, super important. Okay, so let's write down some kind of formulas. One major source of examples of vector fields is can be based on this guy here. So let's stick with the plane. But again, you can imagine this thing works exactly the same in space. Every point has associated to it a vector. All right. Okay, so in the plane, we can look at this vector here, x comma y, right? So this would be a radial vector. So if you're at the point x comma y, the vector would be of length exactly the distance from x comma y to the origin, and it would point radially outwards away from the origin. All right, that's why it's called r. So if you're very close, it would be very short. But again, all of these guys point radially away from the origin. Okay, so this field, field that we talked about, the gravitational field, would be something like this guy here. All right. In fact, something like this. Let me write something like this. So this is, in a way, the prototypical radial vector field. You can take negative of it to point inwards, for example. You can modify it in all sorts of ways. So one thing we can do is something like this. Minus 1 over length of r squared, r over length of r, right? So that makes this guy a unit vector. That's why that's why I wrote it this way. So the length of the vector is actually this guy here, right? And this guy, the second term, expresses the direction. Right, so this is the direction. It's pointing, well, if you include the minus sign, it's pointing inwards. And then this guy here is the magnitude. Okay, so the force of gravity looks essentially like this with some constants. The masses of each of the two objects, m1 times m1 times m2, and then gravitational constant. Okay. So radial vector fields are very, very useful, and you see them a lot in real life. Another vector field that we often see are rotational vector fields. I'm going to write VFs often for vector fields. So that would be something like, in terms of a picture, right? Something like this, where you're rotating, you have at every point, right? You have a vector, and if you kind of put them together, you can see you're kind of rotating around a particular point. All right. We'll be studying these kinds of vector fields quite a bit in future sections. So one typical example here would be minus y comma x. All right. How do I know that this works? Well, this guy here is always perpendicular to, so note minus y comma x is perpendicular to x comma y, right? So this guy is at every point, this vector, the vector at that point is perpendicular to the radial vector. So perhaps it looks like that, right? Which is kind of point in the direction of a circle, right? So it's rotational. Okay, so those are two very big kind of classes of vector fields that we'll be seeing quite a bit. But we actually have many, many examples of vector fields. In fact, anytime we have a function, we can generate a vector field by looking at gradient f, right? So the vector at the point x comma y would be gradient f at x comma y. Okay, so this is called the gradient field, or often called the gradient field. And F in this situation, F is called the potential. Oops. Right? Or a potential function. All right. For example, for the gravitational field I wrote above, if you consider F to be the function f of x comma y equals minus 1 over r, right? Let me write it kind of more precisely. In fact, let me emphasize that we can do this because this is gravity, right? So maybe we do it in 3D. F of x, y, z equals minus 1 over x squared plus y squared plus z squared square root. So this is just distance from the origin, right? Minus 1 over distance from the origin. So this would be a potential for that gravitational field. We love vector fields that have potentials because vector fields themselves are very complicated. If I have a vector field f, right, it's actually comprised of three functions, right? A function which kind of tells you about the direction in the x direction, in the I direction. So let me call it f of x, y. Let me go back to two variables again. I guess I said three, so let me stay with three variables. So f of x, y, z, I, plus g of x, y, z, j, plus h of x, y, z, k, right? So this is a kind of generic vector field, the formula for a generic vector field in space. So in a way, you can see that if you want to work with just a generic vector field, you are kind of doing work with three separate functions that may have zero relations to each other. Okay, so kind of difficult because you have three functions. However, if you're working with a gradient field, then your vector field is actually the gradient of a function, right? And while, yes, there are three components, ultimately, there's only one function that's kind of creating this vector field. So instead of having to study three separate functions, you essentially just need to study this one function, the potential, in order to understand the behavior of the vector field. All right. It bothers me a little bit that I used f here and f up there. So I'm going to call this A, B, and C instead. Okay, so let me just say this is three functions, right? So difficult, right? But again, if you're a potential, if you're a gradient vector field, this is only one function, right? So you only need to understand little f in order to understand capital F. Now, let me emphasize, if f is a gradient vector field, then this. So we really, really like gradient vector fields. So anytime you see a vector field, from here on out, actually, until forever, your first question should be, is this guy a gradient vector field? And if it is a gradient vector field, you're really, really happy. All right. But many vector fields are not gradient vector fields. So you can have a vector field that is not the gradient of a function. All right. That there you cannot, where you cannot find a function whose gradient represents that vector field. In fact, we've seen one already. The rotational vector field, y, x, this cannot be a gradient vector field. How do we know that? Well, as I said, this guy is, let me draw a circle here. This vector field, let me do it kind of dotted. This vector field here, at every point, it's pointing in this direction like this, right? So can this guy, can these arrows represent the gradient of a function? No, because the direction of the arrow is the direction where the function increases. And so this picture would indicate, if this were a function, that as you move along the circle, the value of the function is increasing and increasing and increasing, right? Think about the problem from the midterm, right? So if you're moving in the same direction as the vector here, then your the value of your function is increasing. Okay, so you're increasing, 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 increasing until you get back to here, right, to where you started. But that's illegal, because whatever value it was originally is going to have to be smaller than the value you are now once you've come around, because you've always been increasing the whole time. All right. So you obviously can't have that, because that means that this point right there has two values. All right. And in fact, it has more than two values, because if you go around again, you're going to get even bigger value. So that means that this cannot be the gradient of a function. And so there are indeed vector fields which are somewhat unpleasant to work with. All right. Okay, in the near future, we're going to be trying to figure out how to determine whether a vector field is a gradient vector field or not. All right. However, if you are a gradient vector field, so if f is a gradient vector field, then we do have some nice pictures, right? We already talked about the level curves of a function. So let me draw the level curves of gradient vector field. Let me write it like this, right? Where f is the potential. And you'll hear this word potential a lot in the future in any physics class. And essentially, it always means something like what we talk about here. All right. Okay. So what do we know about capital F? Well, if we have that capital F is equal to gradient of little f, and we draw the level curves of little f, so level curve, level curve, level curve. So then we know the gradient of little f, right, it has to be perpendicular to level curves. So perhaps something like this. It could be in the opposite direction as well, but let's say for the sake of this example that they're all pointing in this direction. All right. So here, perhaps something like this. Again, without the formulas, I only know it's perpendicular. It could be pointing in the opposite direction. But this is a perfectly possible configuration here. All right. Okay. So you can see that the level curves give us a lot of information about, or can potentially give us a lot of information about the vector field that we're interested in. All right. If you kind of follow the gradient, so let's say you're sitting here and you move always in the direction of the gradient, you'll end up with a curve, something like this, where you're always tangent to the gradient vector, right? So let's continue this a little bit more. Gradient vector, gradient vector, gradient vector. Then this is called, at least our book likes to call this a streamline. These are super important, and you'll definitely be seeing a lot of these in differential equations. Because essentially this curve is an integral, in a way, of the vector field. All right. And the level curves in this setting, they're called, or at least our book likes to call them, equipotential curves. Right? They are just the level curves, but perhaps in the context of studying this as a vector field, you can call these equipotential curves. All right, so you'll see that term on the homework. All right, so as a kind of an actual example, perhaps we can look at a function like this, right? X squared minus y squared. We've seen this guy a couple times in the class, and we know that the level curves look something like this, right? This is the this is the zero level curve, and then we have the other level curves kind of like that. And the gradient of this function is going to point something like this. Right, and always remember the gradient points in the direction of greatest increase. And so we can see in this situation, this is kind of like this is a saddle, right? We do have a saddle situation where we have a saddle right there in the middle at the origin. If you look close by, right, in some directions, sorry, I drew all of these in the wrong direction. In some directions, in some directions you're increasing, and in other directions you're decreasing, and that's literally what it means to be a saddle. Okay, by the way, on this line y equals x, and on this line y equals minus x, the vector is zero, is the zero vector, which is perfectly legal. All right. Okay, so one thing that sometimes we want to do is if we have a curve in a vector field, we want to know which points on that curve are tangent to the vector field and which points along that curve are perpendicular to the vector field, right? So maybe we have a curve, let's just say a nice simple curve, a circle here, right, about the origin. Let's give a more concrete example. So let's say this is radius 2. Okay, so this circle here is x squared plus y squared equals 4, right? Our gradient vector field is f equals gradient of x squared minus y squared. So that would be 2x comma minus 2y. All right. Okay, so the question is, where is the curve tangent to f? Where is it normal to f? Normal meaning perpendicular. Okay. All right. So how do you answer this question? Well, this guy is a circle. Our curve is a circle. And so one thing we can do is just parameterize. Or one approach is to parameterize. So our curve is cos t. Actually, it was radius 2, right? So 2 cos t, 2 sine t. All right. So this, let me call this r of t. Right? Our prime of t is minus 2 sine t, 2 cos t. And in our picture above, this vector would be, r prime of t's would be vectors tangent to our circle. Okay, so the question of where is our vector field tangent to the curve is just asking where is r prime of t parallel to 2x, or to, let me call it just capital F. All right. So this is the question of tangent. Let me write like this. So this is equivalent to where is curve tangent to F. Okay, and this guy here now we can solve because we have a literal parameterization, right? So our r prime of t is known, minus 2 sine t, 2 cos t. Oops. Okay. And the f at that particular t is, well, what is our f? It was 2x minus 2y, 2x comma minus 2y. And so our f is 2 cos t, that's x, right? Sorry, 2 times 2 cos t, 2x, comma 2y times 2 sine t, right? So this was my x, this is my y from my parameterization up here. Okay, so now we're just asking when are these two vectors parallel? These two guys, when are these parallel? Okay, so they're parallel if you can, if they point in the same direction. So if they're, or opposite directions. So if they're constant multiples of each other. All right, so they're parallel if this number is a constant times this number, and this number is the same constant times that number. So it becomes an algebra problem. All right. Okay, so if you want to work it this way, you can, and you can solve for it, no problem. The other question of where is our curve normal to f, where is it perpendicular to f? Well, same idea, right? Where is curve normal to f? That's the same as asking, let me put this in a box like that. That's the same as asking r prime of t, where is r prime of t perpendicular to f? Okay, so in this case, you would take the dot product of the two guys, and you would look for where they're equal to 0. All right, so again, that just becomes an algebra problem. Okay, an alternate way you can look at this, because we're in the plane, because we're in 2 dimensions, we can actually take a slightly different perspective. Let me redraw the situation here. Here's our level curves. Here's our vectors. Our vector field, sorry. I should say it like that. And here's our circle, right? An alternative approach to parameterization in this particular setting is that we know that if we can write this circle as a level curve of a 2-variable function, then automatically the gradient of that function is automatically perpendicular to the circle, right? So if I look at g of x comma y equals x squared plus y squared, then gradient of g is equal to 2x comma 2y as a vector. And in terms of a picture, the gradient of g would be vectors pointing out like that. Okay, so now the question of finding points where capital F is parallel to your, is along the curve, or capital F is perpendicular to curve, can be rephrased in terms of gradient g. Okay, so for example, if we want to know where is capital F tangent to the curve? Well, capital F is tangent to the curve. That's the same as saying capital F is perpendicular to the gradient, right? Because the gradient is perpendicular to the curve, right? So if I have a curve like this, tangent to the curve looks like that, and then gradient g I know always looks like that. It's always perpendicular. All right. So this maybe is the easier way to do the problem, right? We know capital F was 2x comma minus 2y, and we know gradient g is 2x comma 2y. And so when are they perpendicular is the same as asking us to solve 2x comma 2 minus 2y dot 2x comma 2y equal to 0, right? And that's the same as x squared minus y squared equals 0. I guess technically it should be 4s in front of these, but they're all just going to cancel out anyway, which is the same as x squared equals plus or minus, let me say x squared, this should be a minus here. 4x squared minus 4y squared. X squared equals y squared, right? And so we've got 4 points in our picture, right? Because this means, this means x equals plus or minus y, okay? So on our circle, we're only interested in points on our curve. We've got 4 points where x is equal to y. So these are going to be our 4 tangent points, right? Where the vector field is tangent to our curve. Okay, and in fact, of course, it's going to be, because this is where our vector field, if we look at a picture of our vector field again, this is going to be where our vector field is 0. All right. Okay, so that's 2 perspectives for solving this problem. But ultimately, it's all based on interpreting, the words tangent, the word normal, and then boiling it all down to algebra. Okay, so this is just an introduction to vector fields. We're gonna start seriously working with them next time, where we're gonna be integrating vector fields in a way along curves